Okay, let's dive into this. $2,000. That is the total API compute cost it took for Astra's multi-agent architecture to coordinate over hours and days, hypothesizing, checking, and revising, to eventually spit out a 249-page manuscript of genuine, earth-shattering mathematical breakthroughs. We're not talking about millions of dollars of supercomputer time here. We're literally talking about the price of a high-end laptop to unlock secrets of the universe that have totally stumped the greatest human minds for years. Is this the price to make human mathematicians obsolete? I mean, that really sets the existential stakes here, doesn't it? Because these aren't just parlor tricks. Astra provided proofs that fundamentally strengthen the theoretical foundations of lattice cryptography. Specifically, it proved polynomial factor hardness for the closest factor problem, which is actually used in NIST post-quantum cryptography standards. Before this, producing this level of elite, highly specialized knowledge was thought to require tens of thousands of dollars in elite human labor, massive grants, and years of graduate research. And now, well, that barrier has entirely collapsed.
Section 1. Machine-verified Lean-4 proofs.
So we have to be absolutely clear about something right off the bat. Astra is not a chatbot. You don't just type a prompt and get a result 3 seconds later. This is a multi-agent system that acts like a tireless, full-time research team, generating verifiable outputs across some seriously extreme, specialized challenges. Take a look at the fields Astra conquered: group theory, operator algebras, lattice cryptography, and quantum complexity. It tackled all of these simultaneously. Astra was acting across 7 distinct mathematical fields in total. It's wild. Let's zoom in on the headline results here. A Sophic group. Now, by definition, a Sophic group is a mathematical group whose structure can be approximated by finite permutation systems. Basically, think of it like shuffling a finite deck of cards, okay? Back in 1999, mathematician Mikhail Gromov posed a really tricky problem. Do non-Sophic groups even exist? Because every single group anyone had ever examined turned out to be Sophic. For 27 years, elite human mathematicians couldn't find a single exception. But Astra did. It actually built a non-Sophic group. It found the first ever exception. Now, you might be wondering, how do we know the AI isn't just hallucinating all this? Well, that brings us to the Lean-4 certificate. Astra didn't just spit out a bunch of text. It produced files that are completely buildable with the Lean-4 compiler, and it achieved what's called a zero sorry count. See, in mathematical formalization, a sorry is essentially a placeholder for a missing step. Basically, a way to say, I'll figure this out later. Astra left 0 gaps, absolutely no handwave steps. Every single part of these proofs is a machine-verifiable proof that can be totally audited by an independent compiler. You don't have to blindly trust OpenAI, and you don't even need human referees to verify it.
Section 2. Community reactions, awe, and dread.
So when you casually drop 10 formally verified, long-standing mathematical proofs onto the academic community, how exactly do they react? Well, as you'd expect, this undeniable proof of AI's elite capability triggered a profound dialectic of pure awe and intense dread across the academic world. Take Jean-François Puget, for example. He says, if I were to start a PhD now, I'd probably look for something with a large physical world component, rather than something purely symbolic. He's arguing that aspiring researchers really need to pivot toward the physical sciences, stuff like wet labs or robotics. Why? Because LLMs are just rapidly swallowing purely symbolic realms, like math and computer science whole. And then we have the darker side of the coin, the existential dread. Fernando Breddi puts it like this: we will live in a demon-haunted world, full of marvelous devices whose operation we will not understand. It's this chilling realization that humanity is fundamentally losing its grasp on the frontier of its own technological and mathematical discoveries. We're stepping into an era where machines are going to hand us these perfect, verified answers. But the human mind? Well, we might no longer even be capable of understanding the journey of how those answers were reached. Now, what's really interesting about this slide is how NYU math professor Scott Armstrong breaks that tension. He says, nobody needs to jump out the window, chill out. It is cool if we can build machines to accelerate our understanding. He brings this incredibly grounding perspective. Look, we are just a bunch of apes trying to comprehend the universe. We shouldn't tie our self-worth to our cleverness. Math is about understanding, and if we can build machines to accelerate that, we should totally embrace it, not panic over it.
Section 3. Economics of AI publishing.
Let's look beyond the bruised egos for a second, because there is a very tangible economic shift happening here that alters the entire publishing ecosystem. Look at the traditional academic model.
Producing a paper costs tens of thousands of dollars when you factor in researcher salaries, time, and university overhead. The main bottleneck? Human writing and experimentation. But welcome to the new AI era. That production cost plummets to a mere $2,000 in API compute. The financial barrier drops completely, and the bottleneck shifts entirely away from human drafting, moving instead toward verifying the original artifacts. But this cost collapse, it introduces a massive vulnerability, the AI slop threat. When the financial and time barriers to producing a paper drop to near zero, it financially encourages researchers with minimal genuine contributions to just flood academia with low-quality AI-generated submissions. We are already seeing hallucinated references completely bypassing basic checks. To survive this, journals and institutions have got to urgently shift their evaluation away from just reading published text and move entirely toward formally verified artifacts, exactly like those Lean 4 certificates Astra just provided.
Section 4. Tao's Vision, Big Mathematics. And this brilliantly illustrates how the mathematical community might actually adapt and save itself from this academic dread. Fields medalist Terence Tao offers this incredible collaborative framework he calls Big Mathematics. Think about traditional mathematics. It's historically operated like a lone artisan, a craftsperson making one beautiful toy at a time, completely in isolation. Tao's vision of big mathematics replaces that with highly specialized AI factories. In this new world, humans dictate the creative direction, but the AI factories handle the lion's share of the technical grunt work and formalization. But Tao issues a really vital warning here, making a strict distinction between artificial friction and natural friction. Artificial friction is the tedious stuff, the routine computations, the literature reviews, the basic coding. We absolutely must use AI to offload that, but we have to strictly protect natural friction. That's the genuine conceptual difficulty, the struggles, the mistakes, the dead ends where young mathematicians actually develop their intuition and their taste. If we let an AI just smooth over that natural struggle, we rob the learner of their foundational understanding entirely. Section 5. The Human Purpose of Math. This brings us to a really profound philosophical question. If machines can eventually handle all the creative and technical heavy lifting, what is the ultimate purpose of the human mathematician? Computer scientist Bharath Ramsundar has a great take on this. He says, a robot that can say, chant the Vedas 1,000 times faster than a human isn't terribly useful, nor would you think of that robot as a repository of wisdom. For many, math is a spiritual discipline. It's like meditating. Pure speed and computation, totally stripped of the human experience of discovery, it completely misses the point of why we do math in the first place. So the crucial point is really captured by Terence Tao here. He says we can electronically reproduce music with perfect fidelity, and yet we still value in-person concerts because we value human connection. It's so true, right? Even if an AI can generate utterly flawless, perfect mathematics, the discipline has always, fundamentally, been about human connection. It's about humans communicating understanding to other humans. If machines can flawlessly solve the universe's most complex problems, what is the ultimate value of human understanding? Astra has proven beyond a shadow of a doubt that the frontier of discovery is changing forever, and the cost of answers has plummeted to almost nothing. But perhaps the journey of understanding those answers remains exclusively ours. Thank you so much for joining me for this explainer. Keep questioning, keep learning, and hey, keep protecting that natural friction.